ballast in a fluorescent lamp has two main functions. Firstly, it limits the current flow through the lamp to a predetermined safe level. Fluorescent lamps have a negative resistance characteristic. Without a ballast, the current would increase unbounded, potentially destroying the lamp. Secondly, some magnetic ballasts include a preheat coil. This coil heats the lamp's cathodes before current is applied, which helps them emit electrons more readily for easier starting. When a fluorescent lamp is turned on, a high inrush current occurs, potentially several times the normal operating current. This is due to the ballast inductance. The ballast limits this inrush current to prevent premature lamp failure and damage to other electrical components. Turning off fluorescent lamps during breaks can save energy, but the savings might be small compared to the energy needed to restart the lamps. Switching off lamps for short durations, like 10 minutes, may not save much energy because the ballast still consumes power. However, turning off lamps for longer periods, like 30 minutes, can lead to some energy savings, although restarting the lamps requires more energy than keeping them on for that time. Frequent switching on and off of fluorescent lamps can shorten their lifespan. However, brief shutdowns of 10 or 30 minutes may not significantly impact lamp life. Turning off transformers during weekends and between shifts can reduce core losses. Core losses occur when the transformer is energized but not supplying power to a load. However, the energy savings might be minimal unless the transformers are significantly underloaded. It is generally recommended to leave fluorescent lamps on during short breaks to optimize energy savings and lamp life, avoiding frequent switching. However, turning off large transformers during extended periods of non-use can save energy by reducing core losses. For a deeper understanding, let's examine current limitation in more detail. The ballast acts as a choke, limiting the alternating current that flows through the fluorescent tube. Without this limitation, the lamp's resistance would decrease as it heats up, causing the current to increase uncontrollably until the lamp fails. The ballast design, whether magnetic or electronic, determines how effectively it limits this current. Magnetic ballasts use an inductor to impede current flow, while electronic ballasts use electronic circuitry for more precise current control. Preheat function, specifically within magnetic ballasts, plays a crucial role in lamp starting. Before the lamp ignites, the ballast sends current through the filaments at each end of the tube. This preheating process vaporizes mercury within the tube, which is essential for proper lamp operation. Without preheating, a higher voltage would be needed to initiate the arc, potentially shortening the lamp's life. The inrush current is a transient phenomenon that occurs when power is first applied to the lamp circuit. The ballast, being inductive, resists the sudden change in current, resulting in a momentary surge. This surge can stress the lamp's electrodes and the ballast itself, so the ballast is designed to withstand these surges and limit their magnitude. Energy-saving strategies should consider the type of ballast used. Older magnetic ballasts consume more power than new electronic ballasts. Replacing magnetic ballasts with electronic ones can significantly reduce energy consumption. Furthermore, dimming fluorescent lamps when full brightness is not required can also save energy. This is more effectively done with electronic ballast designed for dimming. The lifespan of a fluorescent lamp is affected by several factors, including the number of start cycles. Each time a lamp is started, its electrodes are subjected to stress, which gradually degrades them. Frequent switching on and off, therefore, can shorten the lamp's life. However, the impact of short off periods, like 10 or 30 minutes, may not be as significant as longer or more frequent cycles. Transformer core losses are due to hysteresis and eddy currents in the transformer's core material. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the core during each alternating current cycle. Eddy current losses are caused by circulating currents induced in the core by the changing magnetic field. These losses are present whenever the transformer is energized, regardless of whether it is supplying a load. When determining whether to turn off a transformer, consider its size and load factor. Smaller transformers have relatively higher core losses compared to their full load capacity. Therefore, turning off a small, lightly loaded transformer can yield noticeable energy savings. Larger transformers, on the other hand, may have lower core losses relative to their capacity, and the savings from turning them off may be less significant. In addition to core losses, transformers also have copper losses, which are proportional to the square of the current flowing through the windings. These losses only occur when the transformer is supplying a load. Therefore, reducing the load on a transformer will reduce copper losses, but it will not affect core losses. Modern lighting systems often incorporate advanced control strategies to optimize energy efficiency. These strategies include occupancy sensors that automatically turn off lights when a space is unoccupied, daylight harvesting systems that adjust light levels based on available natural light, and programmable timers that schedule lighting based on occupancy patterns. Implementing these strategies can significantly reduce energy consumption without compromising lighting quality or occupant comfort. When evaluating energy-saving opportunities, it's important to consider the overall system efficiency, not just individual components. For example, replacing an inefficient fluorescent lamp with a more efficient LED lamp can save energy, but the savings may be offset if the lighting control system is not properly configured. Similarly, optimizing transformer operation may require upgrading the distribution system to reduce voltage drops and improve power quality. To recap the function of a ballast, firstly, it provides the necessary starting voltage. A fluorescent lamp requires a higher voltage to initiate the arc than it does to maintain it. The ballast provides this initial voltage surge. Secondly, it regulates the current. Once the arc is established, the ballast limits the current to prevent the lamp from overheating and failing. Inrush current, as mentioned earlier, is a brief surge of current that occurs when the lamp is first turned on. The magnitude of the inrush current depends on the ballast type and the lamp characteristics. Electronic ballasts typically have lower inrush currents than magnetic ballasts. Frequent switching affects lamp life because each start cycle puts stress on the lamp's electrodes, gradually eroding the emissive coating. This erosion reduces the lamp's ability to start and maintain an arc, eventually leading to failure. The impact of switching on lamp life depends on the frequency and duration of the cycles. Frequent short cycles are generally more damaging than infrequent long cycles. Transformer core losses are constant losses that occur whenever the transformer is energized, regardless of the load. These losses are due to hysteresis and eddy currents in the core material. Hysteresis losses are caused by the energy required to repeatedly magnetize and demagnetize the core during each alternating current cycle. Eddy current losses are caused by circulating currents induced in the core by the changing magnetic field. Transformer copper losses are variable losses that depend on the load current. These losses are due to the resistance of the transformer windings. Copper losses increase with the square of the current, so they become significant at high loads. When considering energy savings, the trade-offs between lamp life and energy consumption should be considered. Frequent switching reduces energy consumption but also shortens lamp life. The optimal strategy depends on the specific application and the cost of electricity and lamp replacements. In some cases, it may be more cost-effective to leave the lamps on, even when the space is unoccupied for short periods. In other cases, it may be more cost-effective to switch the lamps off, even if it reduces lamp life. Furthermore, the type of ballast will affect savings. Electronic ballasts are more efficient than magnetic ballasts and also have lower inrush currents, which can extend lamp life. Therefore, upgrading to electronic ballasts can be a cost-effective way to reduce energy consumption and improve lamp performance. The size and load factor of a transformer are key considerations when determining whether to turn it off during periods of non-use. Small, lightly loaded transformers have relatively high core losses compared to their full load capacity. Therefore, turning off a small, lightly loaded transformer can yield noticeable energy savings. Large transformers, on the other hand, may have low core losses relative to their capacity, and the savings from turning them off may be less significant. In addition to the size and load factor, the frequency and duration of non-use periods should also be considered. If a transformer is only going to be off for a short period, the energy savings may not be enough to justify the cost and inconvenience of turning it off and back on. However, if a transformer is going to be off for an extended period, the energy savings can be significant. When making decisions about energy saving strategies, it's important to consider the potential impact on equipment reliability and performance. Frequent switching of lamps and transformers can stress the equipment and potentially lead to premature failure. Therefore, it's important to weigh the energy savings against the potential costs of equipment repairs and replacements. Modern energy management systems can help to optimize energy consumption and minimize equipment stress. These systems can monitor energy usage, track equipment performance, and automatically adjust settings to maximize efficiency and reliability. For example, an energy management system can be used to schedule lighting based on occupancy patterns, turn off transformers during periods of non-use, and optimize voltage levels to reduce energy consumption. Understanding the intricacies of ballast function, inrush current, lamp life, transformer core losses, and other factors is essential for implementing effective energy-saving strategies. By carefully considering these factors and using appropriate energy management systems, it is possible to reduce energy consumption without compromising equipment reliability or performance. It is also important to note that local codes and regulations may impact energy-saving decisions. Some jurisdictions have specific requirements for lighting and transformer efficiency, and it is important to comply with these requirements when implementing energy-saving strategies. For example, some jurisdictions require the use of electronic ballasts and fluorescent lighting systems, while others have minimum efficiency standards for transformers. Consulting with a qualified electrical engineer or energy consultant can help to ensure that energy-saving strategies are implemented safely and effectively and in compliance with all applicable codes and regulations. The information provided here serves as a guide.